So we are going to use Newton's equation to find dark matter. So basically, we know that we can observe regular matter, the orbital motion of regular matter, and then calculate the amount of matter that it is being influenced by, right? So for instance, let me go ahead and show you this little applet. And so looking kind of face down at our solar system, at just the first 4 terrestrial planets, we can go ahead and, based upon the velocity, how fast the planet is orbiting, so for instance, let me pick up Mercury here, we can deduce that within Mercury's orbit we have this amount of mass, according to Newton's equation, like this. Well, let's go ahead and scrap that and pick up, let's pick up the Sun, Mercury, and pick up Venus. And how much mass do we have encompassed by that radius? Check it out. It didn't go up much. Well, that's because within our solar system, as it formed, the Sun got most of the matter. So let's go ahead and do the other terrestrial planets, just for kicks. Oh, this isn't going to want to reset. Come on, reset. There we go. Let's pick up the Earth. And there we go. And it didn't go up much at all. Of course, the most massive planet in our solar system would be Jupiter. And so actually we find kind of the neatest dance between Jupiter and the Sun. Oh, it's not going to want to do this. But if I were to go ahead and encompass that last cute little red planet out there, Mars, we'd see that there's not much more matter encompassed by that radius. So another thing then, as far as, I guess I should say, what we do to kind of show the whole situation is come up with what we call a rotational curve. And one of the things that Kepler said was that the farther away a planet is from the Sun, the slower it moves in its orbit. Now, it's not just because it takes more time to complete an orbit because its orbit is larger. Literally, it moves more slowly in its orbit. So let me kind of show you this. I like this one. I have to. So let me click on, of course, this is Mercury. This is how fast it moves. And then going out, and you'll see it kind of drawn on the plot there. Going out, that would be Venus, and going out, that would be the Earth. So notice that its velocity slows down. And that's a direct relationship to the fact that in this particular system, the mass is concentrated with the Sun. Does that make sense? Okay, so this is what we call a rotational curve for our solar system. And we're going to see here in a minute, I mentioned that the Milky Way Galaxy has a lot of dark matter, and actually we're going to look at the rotational pattern of the disk stars to get a fix on the mass within the Milky Way Galaxy. So, okay, so again, within this system, this is kind of unique to our galaxy in that all of the matter is basically concentrated in the center. Well, here's another rotational curve. And this rotational curve, if you go back to your childhood days, remember the smallest merry-go-round, and it kind of makes me kind of dizzy just looking at it. Those little saucer merry-go-rounds is the ones I'm thinking of. But we can talk about the rotational curve if you're on various spots of the merry-go-round. Now, this is a little bit different because regardless of how close to the center of the merry-go-round you are, you have the same what we call angular velocity. But you'll have, because you have to sweep out a larger area, you'll have a different velocity per se. So notice then that we have a rotational curve depending upon how close to the center of the merry-go-round you are, like this. So its rotational curve, again, if you're close to the center of the merry-go-round, you'll have a small orbital speed. Getting near the farther out to the edge of the disk, the merry-go-round, you'll have a greater speed. This is just to kind of show you a different rotational curve. This is as if all points, and I should say all points are kind of rigidly connected. Okay, so let's now go ahead and go from our solar system, to merge around to a galaxy. So we can actually go ahead and say those disk stars, we can go ahead and plot, as I mentioned a minute ago, plot the motion of those disk stars in our Milky Way galaxy. Let me show you what they look like. I'm going to show you first the rotational curve and then the distribution of mass. So isn't this neat? So here we go. Here I am in the supermassive black hole, Sagittarius A star. Okay, notice that I'm going to kind of click a few of these. Notice that this kind of looks like the merry-go-round, doesn't it? Okay, it kind of looks like they kind of orbit rigidly. Now this is how fast those stars are going relative to being, like I said, in the supermassive black hole. So here, let me kind of go outwards now. I'm going out on the disk, getting farther and farther away from the supermassive black hole. And what we see is basically the velocity of the stars just kind of peters out to a constant velocity. These disk stars do, which is different than we see with the motion of the planets in our solar system. So if we go ahead and apply Newton's law, Newton's equation, to what we see with our disk stars, we can then calculate where the mass is distributed in Milky Way Galaxy. And I'm going to show you that as with this little applet, but like the slide says, what we see is that there is matter that we don't see, so it's dark matter, and it's influencing the motion of those disk stars. And where is this matter? Well, this matter is mostly located in the halo region of our Milky Way Galaxy. So let me show you then. And just like we did before, we can, for any given star, let me go ahead and I'm going to draw a circle, let's see, kind of from the center of our galaxy out. And we can look at a star there and look at its rotation, and this is how much mass then is encompassed within the orbit of that star. Let me go ahead and make my circle larger. Okay, this is how much mass is encompassed within the radius of that star. Let me make my circles larger. Okay, so in other words, you know, I'm getting out here kind of to the edge of the disk of these stars, and I'm still going up with regard to the matter that's contained by that radius. Oh, see, it's not getting, you know, we have more and more matter, and that actually is when the first astrophysicists saw it, might have been disturbing or exciting, I'm not sure. But, or it could be that they knew that there was dark matter there. Because my point is that there's matter there, but we can't see it. We can see its influence, but there is definitely matter there. We can't see so much dark matter. So notice then, now this is my favorite. Let me go ahead and do one more. I'm going to go ahead and encompass now, you know, it's from the center out, to encompass parts of the galaxy that have no stars. Oh, darn it. All right. So here we go. Parts of the galaxy that have no stars. You see how this is? Okay. So there's matter there, and that matter has mass, but it's dark matter. We don't see it. Isn't that neat? So this is representing, looking at the Milky Way Galaxy, our galaxy edge on. And so you can see the nuclear bulge. And actually we are about right here, about 27,000 light years from the galactic center. And so based upon the motion of our star, the sun, as it moves about the center of our galaxy, we know that within our star's orbit there is about a lot of mass, about 1 × 10 to the 11th solar masses. Well, the entire mass of the Milky Way Galaxy is about a factor of 10 greater, 10 to the 12th solar masses. And that may not look like much, but if you do the subtraction, that means that mass that is not within the sun's orbit. And remember, the sun is about halfway from, from the nuclear bulge out to the edge of the disk of our galaxy. So that means that there's 90% of the mass is actually not within, associated with our galaxy, is not within the sun's orbit. Okay, so there's just a lot of matter out there that's dark matter. That's my point. And so actually that's what this is trying to show you. If the little blue thing, and one of the things about this course is to me, it might make you feel very small, because what this is representing, edge on, is the Milky Way Galaxy. And you can think of maybe those red stars as being globular clusters. And so the gray stuff, okay, is actually the distribution in general of dark matter in the halo region, clear outside the halo region of our galaxy. Is that crazy or what? Well, we can measure the orbital pattern of stars in the disks of other galaxies. And this just to kind of remind you, a technique we've used before is the Doppler effect. And we can, for instance, if we're looking at the disk of a galaxy that's not really edge on, but not really face on, so we get sort of this sort of kind of orientation, then a star over here, a star A, from our perspective, will have radial motion coming towards us, so we'll see a blue shift. Okay, star B will see no shift, and star C will see a red shift because it's going away from us. So in this way, we can measure the velocity of stars as they orbit in distant galaxies, as they orbit their supermassive black hole. And then again, from their velocity, we can deduce the amount of matter contained within. Then we can come up with a rotational curve. So what you're looking at are 4 different galaxies and their rotational curves. And do they look? They look very relatively similar to the Milky Way rotational curve, where they have this characteristic kind of almost a rigid motion here near their supermassive black hole, kind of like the merry-go-round that we saw. But then their velocities kind of flatten out. And that's because these other galaxies are also surrounded by dark matter that's influencing their motion. So not all galaxies have their disk component dominates. Elliptical galaxies, they're a little bit different when it comes to gauging the velocity of stars in them, because, well, they just are. But this is just simply showing you kind of in general, we can also come up with orbital motion for a star within an elliptical galaxy as well. And what we find is that elliptical galaxies, like spiral galaxies, have like this massive amount, no pun intended, a large region in which dark matter hangs out.